Okay, so now we're going to switch topics a little bit and start discussing in more detail curves. So a special case of curves is our straight lines, which we already talked about, but now we want to say some general stuff about more complicated curves. And so one way to think about them, which is more like of a kinematical interpretation, is that a curve is nothing but the trajectory of a particle. So imagine that you have something like this. So at some time you had a particle, and another time the particle is here, another time the particle is here, then it's here. And so again, like you could take like a picture, a photograph at each instant in time, then you put them all together and you get the trajectory of a curve. You get just some curve in space. So I want to think of the entire positions the particle take, all the positions the particle takes as some sort of curve. And so what that means in practice is that again, you can specify any point on the curve by, if you give me a moment in time, if you give me a value for t, that pins down that particle, because the particle has to be somewhere when you give me some value of time. So that means that you can specify a curve by a function of time, and in terms of coordinates, that just means specifying the individual x, y, and z coordinates of the particle. Okay, and again in practice, some of these you already know. For example, a special case of a curve would be one on the xy plane, say r of t being cosine of t, sine of t, right? So in this case, that means that at time 0, you are at cosine of 0 comma sine of 0, which is 1, 0. At time t equals pi over 2, you're here. At t equals pi, you're here. T equals 3 pi over 2, you're here. And so in total, as you may know already, this is the equation of a circle of radius 1. Why? Because in this case, x of t is cosine of t, y of t is sine of t. Okay? And so x squared plus y squared is cosine squared of t plus sine squared of t, which is just 1. Right? And so curves in general, I mean, they would be more complicated than this one, but they look like some functions of t. So for example, this could be another equation of a curve. And so, like, probably this is something you have already done in a physics class, but once you know the trajectory of a particle, you want to extract more information about it, and for that you need the concept of velocity. So let's talk about a bit about velocity. Let's use the same picture. So what's the velocity in this case? Well, imagine that you have the particle here, then you move some amount delta t, and now the particle is here, so the time difference is some amount delta t, which we think as being really, really small. And then there's a relative position vector, right, delta r, which is, I won't even try to write out the formula here. Let me just put it in this place so that it's easier to see. This is like the vector PQ, right? If you think of this as point P and this as point Q. Okay? And so that's the relative, this is the displacement in some amount delta t. And so the average velocity, right, will be the net displacement divided by the amount of time it took you to get to travel that displacement. So this is the average velocity. And the point is, as you have seen before, when you talked about tangent lines in calculus, is that if you had chosen delta t to be smaller, like so maybe delta t being smaller means that you are now here, there's a new relative position vector. If you have chosen delta t to be smaller, there's another new relative position vector. So you should think of the limit as delta t goes to 0 of this average velocity as a vector tangent to the curve, right? Because notice that the relative position vectors look more and more tangent to the curve. So well, right, the physical interpretation of this is that this is like the velocity of the particle but from the geometric perspective, this will yield a vector that's tangent to the curve, right? So meaning that this will be vector tangent to the curve. Meaning that you should think of the velocity vector of a particle as always being something that looks like this. Well, a bit more tangent. Okay. Now, what's great about this formula for the velocity vector is that you don't really need to learn new differentiation rules. Okay, so essentially, you can just see easily that in practice, the way to find if r of t is x of t, y of t, and z of t, then the velocity vector is just computed by differentiating each of the individual coordinates as a function of time. So it's just really dx dt, dy dt, dz dt. Okay? So that means that you don't need to know any new differentiation rules. So for example, this means that if the position vector was like t squared t minus 1 sine of t, then the velocity vector of this position vector is, or this particle is 2t1 cosine of t. Okay? And as you may already know, right, like there's nothing preventing you from differentiating this function one more time. If you differentiate this function one more time, you get the acceleration, right, which is the rate of change of the velocity. But again, the nice thing is that you can just individually differentiate each of the components. Now, the point is that the velocity, right, is related to the tangent vector to a curve Now you can think also about what would the acceleration be related to, what information about the curve does the acceleration tell you. Well, for that it's useful to think about the case of a function of one variable. So for the case of a function of one variable, right, the first derivative was related to the slope of the tangent line, right? In our case, when we have a curve, the first derivative is related to the tangent vector to a curve. So it still has to do with tangent stuff, with some notion of tangency. But then what was the second derivative useful for? It was telling you something about the concavity of the function, right? If you remember, positive second derivative was called concave up, negative second derivative was called concave down. And then what we will find here soon is that the second derivative of the position is related to what's known as the curvature. It has to do with something known as the curvature of a curve. So meaning, for example, what happens if the acceleration is 0? If the acceleration is 0, that means that the object was moving at constant velocity. Remember that a constant velocity curve is a straight line, and straight lines do not curve, right? They do not bend. So that's why you would say that a line has no curvature. There's no acceleration. But on the other hand, if the acceleration is not 0, that means that there's some sort of curvature phenomenon going on. And this is also related to, say, like general relativity and other things, for why you can think of like gravitation, like why acceleration is related to like curvature of space-time and other things like that. But like why they can be made to fit nicely. But yeah, okay, so for now I'll stop here. In the next video I'll show you some rules for differentiating vectors, which will be useful for other things that we will do.